This lecture is on LEDs, which are light emitting diodes. These are diodes that have the ability to give off light when they're forward biased. The circuit symbol for an LED is just like the circuit symbol for a diode that doesn't have the ability to give off light, except there's an addition of these two arrows to indicate that it has light ability. Now, the primary difference between an LED and a regular diode is just that it's still a PN junction. Okay, any diode is a PN junction. However, LEDs typically will have two different semiconductors on each side of that junction. So the diodes we were looking at previously that don't have the ability to give off light, well, you would have silicon as your semiconductor on both sides of the junction, just doped, one side doped P and one side doped N, but it was still silicon was being used as the material, as the semiconductor on each side of the junction. But typically with LEDs you'll have two different semiconductors. For example, and this is just one example of many, the textbook has different pairings of semiconductors for various LEDs. So one example is gallium for the P side and phosphide for the N side. But regardless what semiconductors are being used, the electrons that are on the N side, okay, so the electrons of the N material semiconductor are going to be at a higher energy level than what's on the P side. Okay, so this way, when current conducts through the LED, okay, when we have current flow through the LED, where, as you can see in this diagram here, the higher end of the voltage source is to the P side, which is the anode, as we know, okay, which is the arrow side, as we've talked about, and the lower end of the voltage source to the N side, which is the cathode, okay, which is the line of the symbol. Well, positive charge flow is going to go anode to cathode, like we talked about. Okay, so that's positive charge flow. And that's how we've defined current in this class, just like in your circuit class. But also, as you learned in your circuit class, if the positive charge is going one direction, okay, so this is positive charge flow, well, the electrons are going the other direction, right? Because there's two ways to look at current, either as electron flow or positive charge flow. So the electrons are going to flow from the N side to the P side, so they're going to drop in energy level as they go from the higher energy level side on the N to the lower energy side level on the P. So energy is given off, and as long as that energy gap difference between the energy levels of the N and P side are such that the frequency of the energy that's given off is within our visual spectrum, well, we see that energy given off as light. And what determines the color is the gap, how big that gap is. So, and also the size of the gap is going to determine how much of a voltage drop we have across that junction. So you see, as far as analysis goes, if we have an LED in a circuit and we treat that LED as ideal, okay, if we have an ideal LED that's forward bias, well, we just treat it like a short, just like we treat a diode that doesn't have the ability to give off light. And if an ideal LED is reverse bias, well, we treat it like an open, just like we do an ideal reverse bias diode that doesn't have the ability to give off light. So analysis wise, there's no difference in how you analyze an ideal LED to an ideal regular diode. But you see, what's a little bit different is the actual, and that's what I started to write down here, is that in the actual case, what's different is the amount of voltage that's dropped across a forward bias LED. You're going to have more voltage dropped across an LED than what you have across a diode that doesn't have the ability to give off light. For example, a red LED has a forward bias voltage of about 1.5 volts. A blue LED, it's about 5 volts. Okay, now When you buy an LED, on its data sheet that comes with it, it will have, you know, what the forward bias voltage drop is. Okay, so in a, you know, a real situation, you know, you're out working someplace or you're doing some sort of project, you know, you would just look up and you would see what that forward bias voltage drop is. So you see these are the V gammas, or the turn on voltages for those. And you know, there are various color LEDs between red and blue. Red and blue are the two extremes. If you have a different color, you know, the forward bias voltage will be somewhere in between these numbers. So in our analysis, when we consider an LED to be actual, we represent it as a voltage source of value VFB. Okay, so the only difference from when you're analyzing a circuit that has just a regular diode is that instead of using 0.6 if it's silicon or 0.3 if it's germanium, you would just use these values here. So if it's a red LED, we would use 1.5 volts for our voltage source, and if it's a blue LED, we'd use 5 volts. So a quick example is, let's say we have this circuit here where we have a 4-volt source, 100 ohm resistor in series with the red LED. It should be clear to you that this is forward bias, right? And current's going to flow like this, right? Because current flows anode to cathode as the current's flowing plus to minus of the source. So this red LED will be forward bias. So to find the current that's flowing in this circuit, we would just analyze this circuit here, where we put in a 1.5 volt source to represent the forward bias red LED. So here's our 4-volt source, here's our 100 ohm resistor, and then the red LED is represented by a 1.5 volt source. Again, this was anode, so you put the plus side of the source to the anode like we talked about. So you see the actual current that would flow through this red LED would just be 4 minus 1.5 divided by 100 ohms, and that's going to be 25 milliamps. Okay, if you did the ideal analysis, well, the ideal analysis, we'll just write it down here, ideal, well, the ideal forward bias current, that would just be the 4 divided by 100, right? Because if it's ideal, we represent the forward bias diode with a short, and there's a 0 volts dropped across a short, so the ideal current would actually be 40 milliamps. Alright, and there's additional LED type of problems in the homework that's assigned, but as you saw here, the only difference when you have an LED in a circuit is in the actual case you have a higher forward bias voltage, and therefore that source is going to be a higher voltage than what you would have in the case of a diode that doesn't give off light.